In Chapter 6, we're going to do problems involving kinetic energy and work and potential energy, and we're going to find out that there's easier ways to solve some of the kinematics problems that we've been doing in previous chapters. So let's start off with a problem just involving work. So we have an 8 kilogram package, slides 2 meters down a chute that's inclined at 53 degrees below horizontal. The coefficient of kinetic friction between the package and the chute is 0.4. We want to calculate the work done on package by friction, by gravity, and by the normal force, and what's the net force on the package. So first of all, let's draw a picture of what we have. We've got a ramp, and we're told that the ramp is inclined at 53 degrees below horizontal, so that means that angle is 53 degrees there. And our package slides down the ramp. Okay, what forces do we have? We've got force of gravity down. We've got the normal force perpendicular to the ramp, and we've got the frictional force like this. Okay, so I want to find the work done on the package by friction. Remember, work is equal to the force times distance times the cosine of the angle between the force and the distance. Okay, so the distance is 2.00 meters. The force in this case is the force of friction, which is mu k times the normal force. And I know mu k, but I don't know the normal force, so I'm going to have to figure out my forces. And the angle between the displacement, which is down the ramp, and the frictional force is 180 degrees. Okay, so let's figure out what our forces are. We're going to have to do our table with our three forces. So I've got my normal force is all in the y direction. My frictional force is all in the x direction. And my gravitational force, some of it's in the x direction, some of it's in the y direction. Now this angle here is 53 degrees. So that means that angle there is 53 degrees, and that angle is 53 degrees. So if I look at my gravitational force, or my weight, this is the x component, that's the y component. X component is sine, y component is cosine. So for the weight, I've got mg sine theta for x, and minus, because it's down, mg cosine theta for y. All right, how do we find the normal force? You should know by now. We always find normal force, add up this, and set it equal to 0. So sum of forces in the y direction is Fn minus mg cos theta is equal to 0 because it's not jumping up off the track, it's not falling through the track. So my normal force is equal to mg cosine theta. And you should have noticed that quite often on a ramp, that's what the normal force turns out to be. So I can calculate my normal force, put in my mass, 8.00 times g, which is 9.8, times the cosine of 53 degrees. And I get 47.18 newtons. So what's my frictional force? My frictional force is mu times the normal force. So that's 0.4 times 47.18, which is 18.873 newtons. I'm not going to round anything off yet because I'm not getting to my final answer. All right, so I want to find the work done on the package by friction. So the work done by friction is the frictional force times the displacement times the cosine times the cosine of 180. So frictional force 18.873 times the distance that it moves, 2 meters, times the cosine of 180. Cosine of 180 is -1. So I just get minus 37.746. And the unit for work is joules. And I've got to round that now. I've got 3 significant figures for everything, so that's negative 37.7 joules. Okay, so that's the answer for part A. Part B says, what's the work done by gravity? Well, the work done by gravity is the force of gravity times the distance the thing moves down the track times the cosine of the angle between the force and the displacement. Alright, so let's draw a picture of what we have. We have our force is downwards, our displacement is down the ramp, and I want to know what's the angle between the force and the displacement. So I need that side of the triangle. I know this angle is 53. This angle, that's a right angle triangle, is 90. Sum of the angles has to be equal to 180. Okay, so that means 53 plus theta has to be 90. So this has got to be 37 degrees. Okay, so I put in mg for my gravitational force times the distance times the cosine of 37. And the work done by gravity then is 8 times 9.8 times the cosine of 37. Sorry, times 2. Distance times the cosine of 37. And I get 125.22 joules. And the work done by gravity is 125 point. I got to round that to 3 sig figs, so just 125 joules. Should it be positive or negative? You have to be careful sometimes. If you don't get your angle quite right, your calculator might spit out a positive number where it should be negative. Think about it. Does the force of gravity tend to slow the block down or speed it up? We know that it tends to speed it up going down the ramp, so that should be positive. And similarly, if you look back to A, friction tends to slow something down, and you'll see we got a negative work. So always, again, remember, if a work is positive, the thing's speeding up. If it's negative, it's going to slow it down. All right, part C. What's the work done by the normal force? Work done by the normal force is the normal force times the displacement times the cosine of the angle between the normal force and the displacement. So normal force is perpendicular to the ramp. Displacement is down the ramp. The angle between those is 90 degrees. So it's a normal force times displacement times the cosine of 90, and the cosine of 90 is 0. So I don't even have to bother substituting in my numbers. Okay, I didn't even have to solve for the normal force for this. Anything times 0 is 0, so the work done is 0. And again, remember, we always said if the force is perpendicular to the displacement, that force does no work. All right. What's the net force on the package? That should have been what's the net work done on the package. Sorry, it's a typo. The net work is just the total of all the work, so it's negative 37.7 joules plus 125. And I'm going to keep my sig figs now, 25.22 joules plus 0 joules and so my net work is 87.5 joules.
Hey Tricia, Eunice Russell is mine.
Okay, problem 2. We have a 4.80 kilogram watermelon that's dropped from rest from the top of a 25-meter tall building with no air resistance. We want to calculate the work done by gravity on the watermelon, and just before it strikes the ground, what's the watermelon's kinetic energy and what's its speed. Okay, so normally in chapter 2 we would have used the kinematic equations to find for the speed at the bottom, but now we can just solve for it using the work done by gravity and then the work kinetic energy theorem. So for part A, the work done by gravity on the watermelon, work is equal to the force times the distance times the cosine of the angle between them. So in this case, I've got my force of gravity downwards, my displacement's downwards, so theta is 0. They're in the same direction. So the work done by gravity is mg, the force of gravity, times the distance that it goes down. And we know that that's just the equation for work done by gravity. So the mass is 4.80 times 9.8 for gravity times the distance it falls, which is 25 meters. And so my work is 4.8 times 9.8 times 25, which is 1176. Remember, cosine of 0 is 1. 1176 joules. Should it be positive or negative? Well, it's falling downward, so it's going to speed up. So we'd expect positive work. And I guess I should round that to sig figs. Looks like we've got 2 sig figs, so that should be 1200 joules. All right, part B. What's the watermelon's kinetic energy and what's its speed? Well, let's use work kinetic energy theorem. So work is equal to the change in kinetic energy. Okay, so that's kinetic energy final minus kinetic energy initial. The initial kinetic energy is 1/2 m times v initial squared, and v initial is 0 because we say it's at rest. So that means initial kinetic energy is 0. So kinetic energy final is the same as a change in kinetic energy. So that just means the work done by gravity is equal to the final kinetic energy. So the final kinetic energy is the same as the work done by gravity, just 1200 joules. Okay, so that was real easy. What's the speed? Well, speed, final kinetic energy is 1/2 mv final squared. I know my kinetic energy, I know my mass, so I can find v final. So I've got 2 times kinetic energy divided by m. Take the square root. So twice, and remember, keep your sig figs when you do the calculation. 1176 divided by the mass of 4.8. Take the square root. And I get 22.1 meters per second. And I should round that to 2 sig figs, 22 meters per second. And you could have also found the speed by using kinematics, using v equals v initial minus gt. Using v squared equals v initial squared minus 2g times the distance, and you would have got the same answer. Okay, but this was a much faster way to do it without having to do any of the kinematics that we did in Chapter 2. Okay, let's do a problem with work done by a spring. So we've got a spring, and we know that to stretch it 3 centimeters from its unstretched length, we need to do 12 joules of work. We want to find what's the force constant of that spring. Well, our equation for work done by a spring, or work done on a spring, by U is 1/2 kx final squared minus 1/2 kx initial squared. In this case, x initial is 0, x final is 3 centimeters, which is 0.03 meters. Okay, they tell us the spring is unstretched, so that means initially the displacement is 0. And so that means that this initial energy is 0. So the work done is just 1/2 k times x final squared. We know the work is 12. We know our displacement, and we're trying to find k. So k, rearranging it, is 2w over xf squared. So it's twice 12 divided by 0.03 squared. So we get a reasonably large number there. I'll get 2.67 times 10 to the 4. And the units for spring constant are newtons per meter. So there's my answer for part A, and I got 3 sig figs, so that's good. All right, part B. How much work must be done to compress the spring 4 centimeters from its unstretched length? So now I want to do the same thing, same equation, but now x initial still 0, but x final is -4 because I'm compressing it. Remember, if we've got the spring that's unstretched, this is 0. If I stretch it, that's positive. If I go back, it's negative. Okay, so -4 centimeters, so that's -0.04. So what's the work? It's going to be 1/2 k, which I know, 2.67 times 10 to the 4, times x final squared, 0.04 squared, minus, and since x initial is 0, this term is just 0. So notice here I've got my displacement is negative, but because I square it, I'm going to get a positive number. .0016. And I get a work that's 21.36. I'm going to put that in 3 sig figs, 21.4 joules. And so as you would expect, it takes more energy to compress at 4 centimeters than it did to stretch at 3 centimeters. Okay, next problem. Now I'm going to combine work kinetic energy theorem with a spring. I've got a box. It's moving at 3 meters per second on a horizontal frictionless surface. It runs into a spring. The spring has a force constant of 75 newtons per centimeter. I need to turn that into the correct units, newtons per meter. So I need to do like that, centimeters on top, meters on the bottom. I've got 100 centimeters in 1 meter. So this is 7,500 newtons per meter. And they tell me use the work kinetic energy theorem to find the maximum compression of the spring. Okay, so what I want to do is I want to say initially I've got my box coming along. It's got a kinetic energy that's 1/2 mv squared. I know m and v's. And let's call it v initial. And then it comes along, it compresses the spring, and it stops. So it squeezes the spring in. V final is 0. And while it's doing that, it does a work that's 1/2 k times the amount that it stretches it squared, just like we did in the previous problem. Okay, so if my work kinetic energy theorem is true, then the kinetic energy that it has at the beginning is equal to the work done compressing the spring. So that means 1/2 m v initial squared is equal to 1/2 k x squared. Okay, I've got a half on both sides. I can cancel that out. What am I trying to solve for? I'm trying to find the compression of the spring. So I'm trying to get x. So let's rearrange that. I get x squared is equal to m v initial squared over k. So x is equal to square root of that, m v initial squared over k. And now it's just plugging in the numbers. So pretty simple. I got 6 kilograms. My v is 3.0 meters per second initially. At the end it stopped, of course, so my v final is 0. And my k was 7,500. Alright, so I get 6 times 3 squared, which is 9, divided by 7,500. I get 0.0072 meters. So that is 7.2 millimeters. So the spring does not compress very much. Okay, now we're ramping up the difficulty here. So now I'm going to combine work kinetic energy theorem and gravity and a spring all together. Alright, so let's draw a picture of what we have. We've got a 2 kilogram block. It slides down a ramp that's inclined at 25 degrees to the horizontal. So there's my ramp. The length of the ramp is 1.50 meters. Okay. Then it gets to the bottom, it slides along the floor, hits a spring, and compresses the spring to stop it. Okay, so we want to know what's the speed of the block when it reaches the floor. And then for part B, we want to know how far the spring is compressed when stopping the block. So that's going to be exactly like that last problem that we just did. Okay, so how do we find the speed when it hits the bottom? Okay, so the block starts at the top with an initial speed of 0, and we want to know what's the speed when it reaches the bottom. Okay, so we could do kinematics if we wanted, solve it like problems in chapter 2 and 3, but we want to use the work kinetic energy theorem because that makes life a lot easier. Okay, so work is equal to change in kinetic energy. Okay, so what's doing the work when it goes down here? It's the work due to gravity is equal to the change in kinetic energy, which is going to be 1/2 mv final squared minus 1/2 mv initial squared, and v initial is 0, so that disappears. Okay, so if I can find the work done by gravity, then I can get my v since I know my mass. So what's the work done by gravity? Well, work done by gravity is the force times the distance times the cosine of the angle between the force and the distance. So if I draw my picture, gravitational force is mg straight downwards. I know my mass, I know g. My displacement is 1.5 meters down the ramp. I need to find that angle in there as theta. I know this angle is 25 degrees. So this angle here must be 90 minus 25, which is 65 degrees. Okay, so the work done by gravity is m times g, which is my force, times the distance, times the cosine of 65. So mg, m is 2 kilograms, g is 9.8 meters per second squared. It goes 1.5 meters down the plane, times cosine of 65. So the work done by gravity is 12.42 joules. Okay, so that's the work done by gravity. And by the work kinetic energy theorem, that has to be equal to 1/2 mv final squared. So work is equal to 1/2 mv final squared. So v final, rearrange it, I get twice the work over the mass, take square root. So 2 times 12.42 divided by the mass, which is also 2, square root. And I get a final velocity of 3.525 meters per second. And I should round that, looks like to 2 sig figs. So 3.5 meters per second is my final answer for V. Okay, so that's part A. Part B, how far is the spring compressed? We're going to do exactly the same as what we did on the previous problem. So the kinetic energy initial is equal to the work done by the spring. So 1/2 mv squared is equal to 1/2 kx squared. Okay, again, cancel the 1/2s. So x squared is equal to mv squared over k, or x is equal to square root of mv squared over k. Our mass is 2. V is 3.525. Again, keep the sig figs. Divided by k, we're told the spring constant is 1700 newtons per meter, right up here. Okay, so do the calculation. And I get that it's compressed by 0.121, and it's a distance, so it's meters, or 12.1 centimeters. And I better, let's see, 2 sig figs, so I better leave that as 12 centimeters, or 0.12 meters. Okay, the last kind of question that we have is to do with power. Okay, so power is work over time. Okay, I've got an elevator that's going up 20 meters in 16 seconds. So obviously my time is 16 seconds. The distance it moves is 20 meters. And the mass is 600 kilograms. I want to know the work. And once I got the work and I know the time, I can get the power. So the work, we're working against gravity. So work is m times g times d. So that's 600 kilograms times 9.8 times 20. I get 11,000 I get 117,600 joules, and put that in. The power is equal to the work, 117,600 joules over the time, 16 seconds. And I get 7,350 watts. So you need more than 7,000 watts in order to raise the elevator up. How about if you add passengers? So if I add passengers, what does that do? What it does is it increases my mass. So my new mass is equal to 600 kilograms, the mass of the elevator, plus the mass of 4 passengers. So 4 times 65. So I get 860 kilograms. So all that changes is my mass on top for the work. So 860 kilograms times 9.8 times 20 is my work. Divide by 16 seconds. And I get 10,535 watts. And I need to take that down to 3 sig figs, 10,500 watts. So it needs considerably more power when it's pulling up people in the elevator.